Okay, I welcome you all to my video lecture presentation. Myself C. Ashok Kumar, Professor, Department of EEE, and my course name is Electronic Devices and Circuits, and the syllabus topic for today's presentation is transition capacitance and diffusion capacitance, which comes under the PN junction diode part 4. And the overview of my presentation will go on like this. First, I will be discussing about the transition capacitance, and then I will be discussing about the diffusion capacitance, and I will be recapping the things whatever I discussed. Okay, and these are the textbooks I referred. One is Electronic Devices and Circuits, McGraw-Hill publication. Jacob Billman is other. And next one is Electronic Device and Circuit Theory by Robert Bollisted and Louis Neshelski, and the publishers are Pearson. And third one is Electronic Device and Circuits by Salivahanan and Suresh Kumar, and McGraw-Hill Education. And first topic of my presentation, transition capacitance. Suppose if you take a diode, already we had seen the diode operating modes. One is the forward biasing mode, second one is the reverse biasing mode, and zero bias also we discussed. And this is a diode I am representing like this, and here I am applying the reverse biasing. Operating mode is reverse biasing, and as you know, this is the P region and this is the N region, and here I am applying the reverse bias mode. So in the reverse biasing mode of operation, there will be a capacitive effect that will be exhibited by the diode. What do I mean by capacitive effect? Capacitive effect means, suppose I am writing the equation like this: C is equal to dq by dV. Whenever you are applying any biasing voltage, whenever there is a charge production inside the device in accordance with the voltage variation. That means whenever charge is varied in accordance with the voltage, then that effect is called as a capacitive effect. Okay, so that we will be seeing here. In the reverse bias, the type of capacitance we call it as a transition capacitance. In the same manner, in the reverse bias, in the forward bias, same, once again the capacitive property will be exhibited by the diode, and that is called as a diffusion capacitance, that will be discussed later. Okay, so here as you can see from this figure, this is a PN diode. I am applying a reverse biasing voltage. So in the P region, the majority carriers are holes, and in the N region, this is N region, the majority carriers are electrons. Whenever you are applying the reverse biasing to the diode, what happens here? The majority carriers will be moved away from the junction. As you can see, this is the junction. This is the junction, and as you can see, the holes are moving away from the junction in order to come out of the device. Similarly, here the electrons are moving out of the device, okay, away from the junction. Okay, so that's why, as you can see, at the junction, the depletion region will be formed. Depletion region will be formed by these immobile ions, and negative immobile ion, and this is the positive immobile ions. Okay, so due to this, the dielectric region is formed. Okay, so the width of the dielectric region, let it be W. Okay, so whenever the majority carriers are moving away from the junction, what happens here? The depletion region goes on increasing. Okay, and this depletion region is similar with a dielectric material. Okay, suppose if you take a parallel capacitor like this, a parallel capacitor, as you can see here, two plates are there here. This is one plate and this other plate, and here in between the dielectric material will be there. Okay, which is nothing but an insulator. Okay, so this is one plate, parallel plate, and this is the other plate. Inside an insulating material will be there, that is a dielectric material. Okay, so here if you go for the capacitance formula, the capacitance formula goes on like this: epsilon A by D. C is equal to epsilon A by D. It is if you take the parallel plate capacitor. Okay. So, where epsilon is the permittivity of this dielectric medium and A is the area of the plates, as I already said, this is the left plate and this is the right plate, and D is the distance between the plates. Okay. So when you compare with this parallel plate capacitor with our PN diode under reverse bias, as you can see here, this P region, this total P region is behaving like a plate here, parallel plate, this plate, left plate. And here once again this N region, it is behaving like a right parallel plate. This is one plate, this is nothing but P region, and this is other plate, this is N region. And in between, as you can see, a dielectric material is there. So this depletion region have the property of dielectric material, okay, which is a depletion region which is formed by the immobile ions, which behaves like a dielectric material. So that's why here I can compare the parallel plate capacitor with the diode under reverse bias. Why? Because this P region acts as a left plate and this N region acts as a right plate, okay, of a parallel plate capacitor, and here this insulator between the plates and this depletion region is behaving like a dielectric material. Okay. So that's why here this effect is called as a capacitive effect. Okay. This effect is called as a capacitive effect. So the capacitance formula for a parallel plate capacitor is epsilon A by D. And once again I am saying epsilon is the permittivity of the medium and A is the area of the plates and D is the distance between the plates. Okay. Whenever D is increased, the capacitance will be decreased. Okay. Which is inversely proportional. The distance between the plates and the capacitance are both inversely proportional with each other. So our diode under reverse bias is behaving like a parallel plate capacitor under reverse bias. So that's why here I am writing the formula of this capacitive effect, and here I am representing this capacitance by CT. CT means it is a transition capacitance, that's why I am writing it as CT. So here epsilon A by, so instead of D here, instead of D, distance between the plates, so I am writing the W here. What is this W? W is the width of this depletion region formed by the reverse biasing mode of operation of the diode. So that's why here my formula goes on like this: CT is equal to epsilon A by W. But here this is D, small d, distance between the plates, if it is a parallel plate capacitor, and here I am representing the diode and I applied the reverse bias. So that's why here instead of D, here I should write W. What is this W? W is a depletion region width. This one is the W, width of the depletion region. And as you can see, whenever you are going on increasing the reverse biasing voltage, the W goes on increasing. Okay, the W goes on increasing. Whenever W goes on increasing, what happens to the capacitance? It goes on decreasing. So once again, I can say here CT, which is the transition capacitance, is inversely proportional to the width of the depletion region. So whenever you are increasing the reverse biasing voltage, as per the operation, the depletion region width must go on increasing. So whenever width is increasing, CT obviously it will be decreased. So this particular effect is called as a transition capacitance, which exhibits in the PN junction diode under reverse bias. And let us see the next topic. Before going to the next topic here, how the current is related with this transition capacitance by the basic formulas here. As you know, the capacitive effect can be represented as the variation of the charge deposited in accordance with the variation of the applied voltage, dq by dV, that is nothing but CT, okay, where dq by dV is a change in charge due to change in voltage. So equation 2 is I can be written as dq by dt, okay, and here CT I am writing it as dq by dV from equation 1 into dt by dt. When both will be cancelled and you will be getting 1, that's why dt by dt, numerator dt, denominator also dt. So here I am rearranging this equation like this: dq by dt into dt by dv. Okay. So dq by dt is nothing but the current I, and dt by dv I am writing as it was. So finally the current equation can be written like this: I is equal to Ct into dv by dt, where Ct is the transition capacitance. Okay, let us move to the next topic. One more capacitive effect will be exhibited in the PN junction diode under forward bias. Okay, so that particular capacitance is called as the diffusion capacitance. So here our diode will be forward bias. This PN diode, as you can see. So this is a PN diode. Here I am applying a forward biasing voltage. Okay, same figure here. So as you can see here in the P region, what are the majority carriers? As you can see here, a white ball, those are called as a holes. Why? Because holes are majority carriers. In the N region, N region, so the majority carriers are electrons. Okay, so that's why here these orange balls are there, those are called as a electrons. Okay, so in between at the junction, a depletion region will be formed. Okay, so whenever you are applying the forward biasing voltage, the depletion region will goes on decreasing. Okay, that is a explanation regarding the depletion region. But what happens here? If you observe the polarity of this applied battery, external battery, so this is a positive charge, and the holes which are majority carried in the P type are positive charge. So what happens here? The repulsion happens. Okay, both are of same charge. So that's why these holes will be moved from left to right. Okay, like this, from P side to N side, the holes will move. Similarly, here if you observe the polarity of this battery, this is a negative polarity, and here in the N type, the electrons are there which carries the negative charge. Okay, once again, both are of same charge, repulsion happens. So that's why here the direction of the flow of electron will be, the electrons from N side has to move to the P side. Okay, holes has to move from P side to N side, and electrons has to move from N side to P side. Okay, so in this process, what happens here is, see here. So here the hole is moving from P side to N side. Okay, like. Okay, so here whenever it is moving from P side to N side, this hole, okay, as you can see here, this is the hole. So it loses its majority status and it becomes a minority carrier in the N side. Okay, so whenever it is in the P side, it is a majority carrier. Okay, whenever it is moving from P side to N side, it is called as a minority carrier. Why? Because in N side, the majority carriers are electrons, but holes are minority carriers. So that's why here, whenever the hole is moved from P side to N side, it is called as a minority carrier, injected minority carrier. Okay, the holes will be pushed from P type to N type, and electrons will be pushed from N type to P type. So here electron earlier, which is a majority carrier in the N type, whenever it is moved to P side, it becomes a minority carrier. Why? Because in the P type, the majority carriers are holes. So that's why it becomes an injected minority carrier. Okay, so that's why here, whenever you are applying a forward biasing to a particular diode, what happens here is the holes will be moved from P side to N side, and electrons will be moved from N side to P side. So whenever the hole is moved from P side to N side, whenever it is crossing the junction, so here the electrons will be there which are majority carriers in the N side. So some of the holes will be in recombination with the electrons, and they disappeared with each other after recombination. So that's why here, as you can see, at junction x is equal to 0, the count of holes at the junction is more. Whenever it is moving from junction towards the right side, what happens here, due to the recombinations, as you can see, the concentration goes on decreasing. So this charge which is moved from P side to N side, it is called as a injected minority charge. Injected minority charge. Okay. Holes, whenever holes are moving from p side to n side, that particular charge is called as injected minority stored charge. Similarly, electrons, whenever they are moved from n side to p side, they are also called as injected minority stored charge. Okay. So, finally, whenever you are applying forward biasing voltage, what happens here? Most of the holes will be moved from p type to n type, and most of the electrons will be moved from n side to p side. So, in this process, whenever holes are moving from p side to n side, it is called as a injected minority carrier stored in the n type. Whenever it is moving from p type to n type. Similarly, electron is moving from n type to p type. So, if you want to define that particular electrons which are stored in the p type, that is called as a stored minority charge. Stored minority charge. Injected stored minority charge. So, that is why here, whenever you go on increasing the forward biasing voltage, the injected stored minority charge will be increased. Okay. So, whenever you are increasing the voltage, the amount of charge will be increased. That type of charge is called as injected stored minority charge. Okay. So, as you can see is capacitance, we can write the capacitance like this, dq by dv, the variation of the charge developed inside the device in accordance with the voltage applied. That is nothing but a capacitive effect. Same thing is happening here. We are applying a forward biasing voltage here, and here we are seeing a injected carrier is stored inside the device in both sides. One is p side, other one is n side. Okay. So, whenever you increase the forward biasing voltage, here the injected minority charge developed on n type and p side will be increased. Okay. So, that particular capacitive effect is called as a diffusion capacitance. So, some equation is there. Here I am representing this diffusion capacitance by CD. Okay. Earlier I represented the transition capacitance as CT. Okay. And here I am representing the diffusion capacitance as CD. So, CD is nothing but dq by dv. Okay. So, Q can be written as tau into I. That means T into I, time taken by the electron into I, the current through the diode. So, tau is the mean carrier lifetime of the electron. Okay. Whenever electron is jumped from valence band into the conduction band, it will be stayed there for some time. That is a carrier lifetime. Okay. So, that is why here a tau I am calling it as a mean carrier lifetime. Okay. And I is the current. So, that is why here instead of dq here, numerator dq, I am writing d tau into I. What is I? I equation, what is the diode current equation? I is equal to I naught e to the power of V by eta Vt minus 1. So, here I am neglecting the, if you segregate this equation, if you expand this equation can be written like this, I naught into e to the power of V by eta Vt minus I naught. As you know, I naught is very, very less quantity. That is why here I am ignoring this. Simply I am writing I is equal to I naught into e to the power of V by eta Vt. So, that only I wrote here. D q is equal to tau I wrote, and I, instead of I wrote I naught into e to the power of V by eta Vt by dV. So, if you go for the differentiation with respect to V, the term is tau into I naught into e to the power of V by eta Vt. You will be getting this equation, tau I naught e to the power of V by eta Vt by eta Vt. Why? Because here I am differentiating with respect to V. So, here V is there, that is why 1 by eta Vt will be getting. So, finally, tau into I naught by eta Vt e to the power of V by eta Vt. So, this can be written as tau, this equation I is equal to I naught e to the power of V by eta Vt. So that's why here I naught into e to the power of V by eta Vt, I wrote it as I plus I naught. I naught also I consider. So this can be written as, I am neglecting this once again, I naught is very less quantity, reverse leakage current. So this can be written as tau into I by eta Vt. So tau is the lifetime of the carrier, whether it may be electron or hole, and I is the current through the diode, and eta is the ideality factor of the material. Suppose if it is germanium, the value will be 1. If it is silicon material, the value will be 2. And Vt already we explained about this one. Vt is the volt equivalent temperature. Vt can be written as kT by Q. K is the Boltzmann constant and T is the absolute temperature and Q is the charge of the electron. This can be written as T by 11,600. As you know, the value of Boltzmann constant, and the value of Q, both are constants. If you calculate the values, you will be getting Vt is equal to T by 11,600. T has to be represented in absolute temperature. So finally here CD is equal to tau I by eta Vt. Okay. So this is about the diffusion capacitance. Diffusion capacitance effect is exhibited by the diode under forward bias. So finally the graph related with these two capacitances. As you can see, first let us see about the transition capacitance. As you can see, we are applying the reverse biasing voltage. Whenever we are goes on increasing the reverse biasing voltage, what is happening here? The capacitance goes on decreasing. Okay, C is equal to dq by dV. So whenever the voltage is increased, the capacitance is decreased as per that equation. Similarly here, the forward bias. What about the diffusion capacitance? If you go on increasing the voltage, forward biasing voltage, as you can see here, the capacitance goes on increasing. Why? Because the amount of stored injected charge developed inside the device will be increased. Why? Because most of the holes will be pushed from p side to n side, and most of the electrons will be pushed from n side to p side if you go on increasing the applied forward biasing voltage. And the units of this capacitance will be in terms of picofarads. Okay. So finally, let me recap the things here. So first I discussed about the transition capacitance CT, which is exhibited inside the device under reverse bias. So capacitance is nothing but dq by dV. Whenever a charge is developed inside a device, whenever you are applying a voltage, the charge will be varied in accordance with the developed voltage inside the device. Okay. So the transition capacitance will be observed in the PN junction diode under reverse bias. And also application area is the property which is exhibited in this transition capacitance will be same as in the varactor diode also, where varactor diode is used in the communication in order to tune the radio and TV. Okay. Next, we discussed about the CD. CD is a diffusion capacitance, which will be exhibited in the PN diode under forward bias. Okay. So this is about my lecture, and I will be stopping here, and I will be continuing in the next class with a other topic. Thank you.